So last time we spoke about Monte Carlo methods in general, and we spoke about sort of the idealized case where we can draw independent samples from our distribution. Today we'll be talking about Markov chain Monte Carlo methods. And sometimes Markov chain Monte Carlo is abbreviated to MCMC. Let's quickly review sort of the advantages and disadvantages of sort of general MC methods, or MC methods, I should say, that draw independent samples, and MCMC methods, which, as we will see, do not draw independent samples. So suppose that I have a distribution that I'm trying to draw samples from, and this will be pi of r versus r, pi of r versus r. It's supposed to be the same pi of r. Now, in MC, when I'm drawing independent samples, maybe I draw one sample from my distribution here, then the next sample that I draw is here, and then the third sample is here, and so on and so forth. Then eventually, if I try to collect all of the samples that I drew, and I sort of histogram them, I should be able to kind of reproduce this pi of r, hopefully, this approximate pi of r, reasonably nicely. We note, again, every sample can be drawn from anywhere in this region, but again, if my Monte Carlo methods will ideally mostly draw samples from regions of high density. What about Markov chain Monte Carlo? In Markov chain Monte Carlo, our samples form a chain. So we have to start off by saying, I will start somewhere, and maybe that somewhere where I start is here. Even choosing a point where to start, sort of, and starting to explore your distribution is not a completely trivial task when you have a very high dimensional distribution. But let's go ahead and sort of show what our samples might look like. Our samples will be related to one another, and they will form what's called a Markov chain. This is what we're going to call a Markov chain. So the idea is that I start drawing one sample, we'll call that R0. And then the way Markov chain Monte Carlo is going to work is that we are going to propose to move somewhere else and decide with some acceptance probability as to whether we accept this proposal or not. If we accept it and we move somewhere different, then we end up at some R1. Now suppose that I make another proposal and at this point I reject it. Then my R2 is then at the same location as the R1 because I proposed something and I rejected that proposal. We're going to explain how that happens mechanically shortly, but for now we're talking about this conceptually. Now I propose something different, and at this point now I accept it, and maybe I move a little bit in this direction. That becomes my R3. So the idea is that all of my samples tend to be in one region. Eventually, as I draw more and more samples, I may start exploring this region here. But perhaps, after 8,000 draws, all I will have sampled will be sort of the second peak here, and I won't yet have explored this region here. So it can be a lot less efficient. Now, of course, there's a lot of Markov chain Monte Carlo strategies. Many of them are adapted for specific types of distributions that have, specific forms, properties, and so forth to make things much more efficient. But in general, having correlated samples is always worse than having decorrelated samples. Then the question arises, well, why would I use correlated samples if I can use decorrelated samples? It's always better. It's always more efficient. Well, the answer is, of course, that this requires you to sort of being able to draw samples from distributions sort of directly. And that in general is very difficult. Here, this can be used almost always, but the problem is that it can become so inefficient, it can take the age of the universe. So at some level, you have to pick your poison. The idea is that for most complicated examples where you cannot do MC, you will be doing MCMC, and then you'll be sort of thinking about ways of making MCMC very efficient, even for complicated examples. So with that said, I think it'd be a good idea to start discussing some MCMC requirements. So there's four main requirements. The first one is that the chain, that means the R0 to R1 to R2, the Markov chain must pass, or I should say should be able to pass, through every feasible sample. So there shouldn't be a region of space that you simply cannot explore. When you propose something, you should be able to propose across the entirety of the support of your target distribution, which makes sense. The chain should be ergodic. So that means you should be able to pass between any two pairs of feasible points. That also makes sense, right? It isn't that, you can explore all, but by the time you've made it here, you simply can't go back, right? So these two are related, but they're a little bit different. Finally, the chain must have a stationary density, meaning that if you start exploring and you're generally going in some direction, you can't just keep going in that direction. At some point, kind of the flux from one region to another sort of need to be the same. We'll explain this. This will require some additional, or this will really sort of set what kind of proposal distributions we can use and how we ultimately set our acceptance probability in terms of, accepting or not whether we move. The final condition also is very important, and it also sort of sets how we determine our acceptance probability, and that's that the stationary distribution, or the stationary density, must coincide with the target distribution, which is the pi of r. So the pi of r that you want to draw a sample from should coincide with the stationary density that you're exploring. So at this point in the chapter, we sort of discuss how these two requirements precisely give rise to the acceptance probability, which will be the most important criterion used in MCMC. We won't delve into these in very much detail here. I will only sort of briefly explain that this condition here requires something called full balance. This condition here requires something called detailed balance. Now, in case you're interested in sort of looking at the advanced section for how the acceptance probabilities are derived, detailed balance is a requirement of this condition, and it is a stronger condition than the full balance condition. Therefore, we don't use the full balance and detailed balance. We simply use the detailed balance for both 3 and for 4. So what's going to happen? So how MCMC works, sort of conceptually, and then we'll talk about it, how it works really mechanically, how you can code it up before sort of looking at some computational examples at the very end of this chapter. But the idea is that you start off with some R0, and you come up with some R proposed using a proposal distribution, which we'll talk about. Then you have to decide whether you accept or whether you reject based on some acceptance criterion. If you choose to accept, then R new becomes R proposed. If you decide to reject, then R new is equal to the old R, which in this particular case we had just started was R naught. Now, precisely how we set this acceptance criterion and how we use it in the context of proposing values is what is dictated by conditions 3 and 4 ultimately, and dictated by sort of detail balance. So very briefly, if my proposal distribution has the right support, and generally speaking, it allows for transitions from location to location, then most of the time conditions 1 and 2 are easy to satisfy. It's conditions 3 and 4 that'll really impose the structure on the acceptance criterion. So let's just give one example. Suppose that I want to draw, and again, samples from the following distribution. Looks pretty complicated. Maybe I can start off, and this is, from, in principle, this distribution has support from -infinity to infinity, but maybe here the bulk of the density is from 0 all the way to 15. Let's make it very concrete. Then maybe I can start off with a proposal distribution, let's call it Q, that is proportional to, well, that is a Gaussian. So the Gaussian will start off at some R old, and I'm going to make some proposal, and that Gaussian is going to have some kind of variance. So suppose that I start off at some R old, my R naught, which is somewhere here, and I propose a subsequent value. Now, with equal probability, I can propose a value to the left or to the right, and the size of the jump will presumably be dictated, or the statistics of the size of the jump will presumably be dictated by my variance. So I propose something, and maybe I propose this region here. This will be my R proposed. Then I have to use my detail balance condition, which we'll get to shortly, in order to be able to decide whether I should accept or reject this R proposed. Now what's going to happen is that it looks like I'm going up in probability. And so therefore, this looks like it's, I'm sampling a region which has higher density in my target density, right? So this point here is higher than that point there. So chances are I will accept, and this will become my R new, right? We haven't talked about what the acceptance criterion looks quite yet, but that's generally the logic. Now, my R new for my next iteration becomes my R old. And at this point, I propose a new value. Now, if my proposal distribution is Gaussian, I have 50-50 chance of proposing something to the left or to the right. Now, suppose I propose something to the right, and this is my new R proposed. So I'm going from here to here. I'm going down in probability. That doesn't seem as good. Well, the acceptance probability, again, has to satisfy the stationary condition. So we don't always only accept going in the right direction. Because if that were the case, then I would be moving up, up, and up here. And every time I try going down in order to discover this new peak here, I would say, nope, not allowed going down. So I need to sort of have a stationary density. So the idea is, perhaps I can accept, but with a smaller probability, the possibility of going downhill. So in other words, of going down in probability. And suppose that then I use my acceptance criterion, this step is accepted, and now this proposed now becomes my R new. So then maybe I should call this, at this point, my R1. This is my R new, which at my next iteration becomes my R old, and then I go ahead and I propose again. So that's kind of the logic of how this is going to work. Again, you've noticed that I've kind of focused on this region almost intentionally to make it a point that it's going to take a while before I discover the fact that I have a big peak in density right here, right? That would not happen if my samples were independent. Okay, so with that said, next time we will sort of delve into the mechanics of how MCMC works and the exact mathematical form for the acceptance criterion.